Welcome once again to RF transceiver design course. We are discussing about the basic of phase lock loop. In last class we have seen a type 1 PLL and we tried to derive the transfer function of type 1 PLL. Now we are moving to the type 2 PLL. So, we already have discussed that where the drawback of type 1 PLL is if there is a change in the frequency, then it can not lock the phase. So, if we want to if we have a frequency and phase both is a different, then we need a phase frequency detector. So, if we try to see that how what are the condition for phase frequency detector. Let us say there is a omega A frequency and omega B frequency as shown in the figure. So, this is a omega A and this is a omega B. So, if omega A frequency is high, if omega A is greater than omega B, what will happen that you will have a QA which is increased. So, if omega A is higher than omega B, your QA is increased and the difference in the phase will be observed by the QA and it will start increasing. Now, the moment QA is equal to QB. So, there is a if omega A is equal to omega B, then this QA will have a constant change in the phase, because now there is a frequency which is a constant. There is a possibility that the phi A cannot be phi B, but that will same as a what we have done in the type 1 PLL. So, either QA or QB will constantly give the output. It is depend upon how increase means how the phase difference is. Now, if there is a change in the frequency, let us see if omega B is higher than omega A, then QB will increase. So, in this case, in the figure which is shown, there is a two case only shown. One is omega A which is greater than omega B and omega A which is equal to omega B. So, in the both the case your QB is a constant, there is a no change, there is QB is a constant. But if there is a change, if instead of omega B is greater than omega A, A will look like QB and QB will look like QA, and same will be for the when omega A is equal to omega B. So, here a rising edge on A yields a rising edge on QA. If QA is low, a rising edge on B resets QA. So, if there is a rising edge on B, it is reset QA if QA is a high, and this circuit is a symmetric with respect to A and B. So, either you give to A or B, it is a symmetric. So, how we can implement this mechanism in the circuit. So, if we try to see the state diagram look like this. When QA and QB is equal to 0, there is a 0 state. There is other two state, either QA is a high and QB is 0. So, there is a one state which is a state 0, where QA is equal to 0 and QB is equal to 0. Now, as A means omega A frequency is increased, then QA is equal to 1, QB is equal to 0. It will remain high, QA will remain high up to when omega A is high, when A is high. The moment QB is going to become high, then it will try to go to the state 0. If omega B is high, then QA is 0 and QB is equal to 1, and it will remain constant, it will start increasing QB if uh, B is high, omega B is high, and then the moment omega A is again going to become high, then it will come to the state 0. So, what it's, there is a 3 logical states are necessary: QA, QB is equal to 0, QA is 0, QB is 1, QA is 1, QB is 0, and to avoid a dependence of the output upon the duty cycle of the input, the circuit should be realized by using an edge triggered sequential machine. So, if we try to make a edge triggered sequential circuit, the same PFD, phase frequency detector, we can use a 2 flip flop and AND gate. So, there is a this is a 2 flip flop. Here there is a VDD is applied to the D input and the clock is at the A. Similarly, there is a VDD and a clock. So, it will look same, the D and clock, and when the QA and QB both are equal, it will reset this pulse. So, when QA and QB both are 0, it will reset this clock. So, QA and QB are simultaneously high for duration given by a total delay through the AND gate and reset the path. So, when QA and QB both are 1, it will reset the path of the flip flop, and the width of the narrow reset pulse on QA QB is equal to the 3 gate delays. So, there is a 3 gate delay, one is this and another is due to the 2 gates which is there in the latch 1 and latch 2, and that total delay is depend upon this 3 gate delay plus the delay of the AND gate. So, this is how we can implement the phase frequency detector by using a sequential circuit. So, as A is increasing, and what will happen, that you will get a VDD, means D will be directly D will be get at the output, and as omega B will increasing, you will get a QB which is raised, but the moment both are equal to 1, this will be reset. So, this is how this PFD will work. Now, once we have designed the PFD, what we need is a we need to use a same like a type 1 PLL, the RC low pass filter, and then you need to amplify the difference between these two and the VCO. So, using a PFD in a phase lock loop resolves the issue of the limited acquisition range which was there in the type 1, and at the beginning of the transient the PFD act as a frequency detector and then pushing VCO frequency towards the input frequency, and after that two are sufficiently close, PFD operates as a phase detector. So, it will operate as a phase detector. So, it will both, it will do as a frequency as well as a phase detection. So, in order to do that, means we need in between a circuit which can able to do this up and down, because there is a Q and QB. So, we need to go for up in the frequency or down in the frequency. So, we need a charge pump. So, we need a circuit which is called a charge pump, which will increase the voltage or decrease the voltage depending upon the increasing of QA and decreasing of the QA and QB. So, here in charge pump, this is what will happen, that when QA is high, then it will start charging this capacitor and with the current, and when there is a QB which is high, it will start discharging. So, here switches S1 S2 are controlled by the up and down respectively, and a pulse width of delta t on up turns S1 on for delta t seconds, allowing I1 current to charge C1. So, your V out goes up by delta t into I1 by C1, because it is charging for only delta t period. Similarly, a pulse on down yields a drop in a V out. If up and down are asserted simultaneously, I1 simply flows through the S1 and S2 to I2, creating a no change in a output voltage if up and down are asserted simultaneously. So, then your V out will remain a constant. So, if we want to find out the transfer function, how do we find a transfer function of this? So, there is a we can approximate the PFD or charge pump circuit of a figure which is shown here as a current source and some average value driving a C1. Then we calculate the average value of a current source and the output slope for an input period of T in. So, for input phase difference of delta phi radian, what we get delta phi by 2 pi into T in. So, seconds the T in seconds, and the average current is equal to I p delta phi by 2 pi, and the average slope. So, the average current is this. If we try to find out the average current, and average slope is I p delta phi by 2 pi divided by C delta pi by 2 pi divided by C1. So, the Hs transfer function, which we can write it down, which is I p by 2 pi C1 s into k VCO s divided by 1 plus I p by 2 pi C1 s into k VCO. So, this is a transfer function of this charge pump PLL. Such a loop ideally forces the input phase error to 0, because there is a finite error, and it will lead to unbound value of a V control. So, what we need is we first derive the transfer function of the PFD, charge pump and C1 cascade, and then we call a type 2 PLL because its open loop transfer function contains a 2 poles at the origin. So, now if we want to find the transfer function for PFD, then charge pump and C1, what we get there, we can approximate this waveform by a ramp. So, this is a how the V control is increasing, and that can be considered as a ramp, and its slope is given by I p by 2 pi into C p into delta phi. So, delta V control change in the is given by delta phi by 2 pi T in I p by C1. So, if we write with respect to time, V control T equal to delta phi by 2 pi I p by C1 into T into U t, because it is its slope is also changing with the time. So, T into U t. So, V control by delta phi s equal to I p by 2 pi into C1 s. So, if one of the integrator become a lossy, let us say if this capacitor, the system can be stabilized, and this can be accomplished by inserting a resistor in series with a C1. So, we need to add a resistance R1 C1 that will provide additional stability in the charge pump PLL. So, this is also known as a charge pump PLL, because we required a charge pump circuit. So, now if we want to find out the complete transfer function, here this is a V control where we have approximated as a linearly changing with the time, and above it there is a ripple which is so there is a V control 1 and V control 2 if we decompose like a superposition theorem, and what we will get a V combination of total V control T is a combination of V control 1 and V control 2. So, where V control 1 is delta phi naught by 2 pi I p by C 1 T u t plus delta phi naught by 2 pi I p by C 1 into R 1 into u t. So, this step of the height. So, this initially what we have considered, because there is only capacitor, now this step of this height is depend upon this value of R 1. So, now the V control by delta phi s is given by I p by 2 pi 1 by C 1 s plus R 1, and the transfer function H s is given by this equation, where we are considering the R 1 and C 1 both. So, this is the same similar transfer function which we can find out the damping factor, and the if we compare with the transfer function for the stability, that is s square plus 2 xi omega n s plus omega n square. So, xi will be given by R 1 by 2 square root of I p into k V c o and to C 1 by 2 pi. So, your omega n natural frequency is depend upon I p into k V c o divided by 2 pi into C 1. So, if we try to plot the open loop transfer function, the way we have plotted the open loop transfer function in the type 1 PLL. So, for type 2 PLL, the there is a 0 which is added because R 1 because of R 1 and C 1. So, if the 0 is added, without 0 it will look like this, where it will be constant around minus 180, but with 0 that will phase margin is increasing, and that will help to uh, improve the stability in the circuit. So, here we have tried to address both the problem that we have seen in the type 1 PLL, that is the problem of the phase and frequency and the problem of the stability. So, that both problem can be solved in the type 2 PLL. So, there are more understanding and details are required in order to design the complete PLL. So, as far as this course and this RF transceiver design course is concerned, the PLL is we have tried to understand the PLL just to have the basic idea. If you are interested for more in detail about to understand about the PLL, you can go through the reference book which is provided, and that will help you to understand, and you can also refer the lectures which are on the phase locked loop design. So, these are the two basic type of PLL, PLL 1 and PLL 2. Once you have an understanding of the PLL design, you can also design a frequency synthesizer, and that frequency synthesizer will be useful for generating a different frequencies for a different bands that we have studied, GSM band and then CDMA, or different frequency band for different application, Wi-Fi bands. So, that all can be designed, means synthesizer can be designed for different application, and it will be useful in the transceiver design. So, we have discussed the PLL. Now, charge pump PLL. In charge pump PLL, all the PLL that we have discussed, type 1 and type 2. So, what is the issue? In reality, that when we want to use this PLL in the actual RF transceiver, what we need is a our frequency range. So, we need a frequency synthesizer. So, why there is a need of frequency synthesizer? The first is the VCO frequency range, because we are working at 900 megahertz or 2.4 gigahertz or 5.6 gigahertz. So, different RF frequency, and that frequency are very high. So, the VCO frequency is very high and it is in gigahertz range. But in reality, the practical reference that we use a crystal oscillator, they might be in kilohertz to megahertz range. So, that is a limitation of crystals which we are applying as a reference, and the VCO frequency which needs to be tunable. Uh, so, that is the advantage that VCO frequency can be tuned with the voltage at very high frequency, but we cannot tune the reference. Our reference frequency is a fix. So, this reference frequency cannot be tunable, however, VC output frequency can be tunable. So, what is the solution? The solution is, why can't we use because the reference frequency is small and the output frequency which is high, why can't we divide the output with the number by n. So, here we can divide f out by n. Now, the as PFD we already have discussed that phase frequency detector and after that charge pump. So, this PFD required the same frequency and only the phase difference will be find out. Now, in order to do that, we need this frequency which is coming from this, which is f out by n. So, this is f out by n, and this is f reference frequency. Let us say f reference frequency, if we if this f out by n and this f reference might not be equal. So, we can put another divider circuit here, which is a divided by k, and we can divide f reference by k. So, our f out by n should be equal to f ref by k. So, this both the frequency should remain same. So, what is the output frequency? So, output frequency we can write f out, which is equal to f reference by k into n. Now, this f reference by k, another important thing in RF transceiver design is, we are going to use a different channel in the single band. For example, in GSM band has a 900 kilohertz. 900 megahertz is a center frequency, and its channel bandwidth is around 200 kilohertz. So, how many channels? More than whatever more than 125, more than 125 channels we can include. So, here this channel spacing between these two is nothing but f ref by k, because what we want to do, we want to do the frequency control. So, when we do the controlling from one frequency to other frequency, because we need to select channel 1, channel 2, this channel has a 200 kilohertz bandwidth, and that channel bandwidth is equal to f ref by k. So, that is a channel frequency f channel, and our output frequency is multiplication of n into f channel. So, in that case, if your reference frequency is small, then your n, the n requirement of n will be too high. So, that can be decided based on the what is the application or what is the standard that you are using. Now, if we try to see the Bode plot of the open loop gain Gs as well as the PLL closed loop transfer function Hs. So, how the Gs can be? So, here Gs can be given by K PFD that we have already defined into K VCO VCO divided by S into 1 by N. So, this is a GS transfer function of the this receiver, and what we are adding is a 1 by N. So, this is a GS, and if we want to write a HS, which is given by 5 out by 5 in equal to N to GS by 1 plus GS. So, this is a open loop transfer function, and this is a closed loop transfer function. Now, if we see GS, there is a one if type 1 PLL is there, there is a only one pole. If type 2 PLL is there, we can add a FS, which will add another pole. So, there is a 2 pole, and that because of the 2 pole there is a slope which is a 40 dB per decade. Now, another 0 will come into the picture in type 2 PLL at omega z, and that will help us to improve the stability, that we already have discussed. And this once this 0 will come, again it is a minus 20 dB per decade, and you will get this is a omega u is a unity gain frequency. Now, what is the catching point here is that our N, this if GS for frequency, if GS is much higher than 1, for frequency omega less than omega u, we can have a H j omega is equal to N. So, the Hz is given by the N, and it can be written 20 log of N, and this is a transfer function of 1 by 1 plus G, and which will be reflected the GS and Hz in 1 by 1 plus G transfer function. So, this is how the transfer function of fractional-n PLL, only the difference is here 1 by N, and N will be added. Now, what are the noise sources in the synthesizer? So, if we want to see the noise sources in the synthesizer, if we try to draw this, what are the different noise contribution that happens? So, reference for low frequency, reference will dominate, and it has a slope of 2, and after that, so here reference will dominate, and then up to the PLL bandwidth, it will dominated by the PLL. Again at very high frequency than the PLL bandwidth, the VCO will dominate the noise. So, this is a PLL noise here, and then after that, if there is a buffer, then buffer has a wider bandwidth, buffer will dominate. So, this is how, so here VCO will dominate. So, this is how the noise source, various noise sources will be there in the synthesizer. Now, if we assume a simple loop filter, we can give the transfer function as this. This is a transfer function of fractional-n PLL, and the 2 poles of the transfer function we can write it this. So, for phase noise, overall phase noise, there are a different contributor. If we consider the loop filter, VCO and reference and other things as ideal, then this is a curve of VCO, where at low the phase noise is low at low frequency, it is increasing with the frequency offset, and then again the phase noise will decrease because of the low pass behavior. And as this is a reference has a at frequency offset, reference will dominate the phase noise, and then you can see this is a reference which is dominating the phase noise, and after that what will happen, that VCO will dominate. So, this is a VCO noise, and this is a black curve is a overall phase noise with the frequency offset. So, this is about the integer and fractional and integer and synthesizer. Now, integer and synthesizer has some limitation. So, the integer and frequency synthesizer has a major drawback. What is that major drawback? The reference frequency cannot be higher than the channel spacing. So, there is a channel spacing that we are adding, means by changing the reference, means if we want to change the frequency, it should, that n should change according to the channel frequency. Now, that reference frequency cannot be higher than the channel spacing. So, if it will limits our performance, because channel spacing always will be very small, and that small channel spacing, what will happen, that the required we are dividing the output frequency divided by n. So, you need a very high n, means n requirement is high because your reference frequency is small. And another thing is, when the reference frequency is less, you require settling, means it required high settling time, and the capacitor and resistance value is increasing. So, what will happen? So, this in turn sets upper bound on loop bandwidth, and which causes several implication like size of the loop filter, capacitors and resistor, synthesizer settling time, close in and far out phase noise, and ability to work with any arbitrary crystal oscillator, because you need a frequency which is equal to the channel spacing. So, we cannot use any crystal oscillator, and there are a reference spurs and amount of filtering also is a impacted by a number of n. That is a how much division we are doing. So, what is a solution? If we can do the fractional division of the frequency, and that will help us to get rid of the very get rid of the channel spacing, that minimum reference frequency requirement, and that can be done. So, again the integer and frequency synthesizer can be redrawn. Here this n divided by n and n plus 1. So, how this will work for let us say if there is a k cycle, and for k minus 1 there is a divided by n will happen, and after that for one time n plus 1 division will happen. So, the overall division will be in the fraction alpha. So, this is how we can make the this is how we can make the frequency division. So, that will be around n plus alpha, n plus alpha, and this alpha can be given by the value k. So, we will see how it works. So, here as we have already seen, the main drawback of simple approach outlined here in figure is a creation of the fractional spur. So, how the fractional spurs will be generated? Because this is a reference and this is a divider. This is a hypothetical example, dividing n for 3 cycle and n plus 1 for 4 cycles. So, total k is equal to 4. So, this is a reference, this is a division, this is u and d. So, what will happen that here the up means up and down. So, frequency is up and down, that we can find out. So, here the up is happening when there is a this difference of the reference and division frequency, and your control voltage will start increasing. So, because it should start increasing the frequency by voltage control oscillator, but as the frequency start increasing, what will happen after n up to n cycle, this will happen, and after n plus 1 means after up to 3 cycle, it will divide by n, and after that, so this is 1, 2 and 3 cycle, it will divide by n, then it will divide by n by 2. So, when it is dividing, and it will divide by n plus 1. So, when it is dividing by n plus 1, there is a one spike will come, and what happens that because of this difference, that again will start increasing, and what it happens that due to this it will generate a spur signal, that is called a fractional spurs. So, the PFD starts to generate a down pulse to slow down the VCO, which in turn causes the control voltage to reduce. On the 4th cycle, the VCO is divided by n plus 1, resulting in the divider output to be slower than the reference, and hence up signal is created that raises the control voltage. So, what will happen, this will k is equal to 4 times, this pattern repeats, k is equal to 4 cycle, and it leading to a VCO being modulated by a periodic signal with a period of f rep by k or alpha f rep, which creates a sideband at alpha f rep and its harmonic. So, in reality we want a signal like this, but there is a sideband is created, and that will generate a fractional spurs like this at same alpha, means for period of alpha into f reference. So, here how can we calculate this f out? So, this division can be calculated as, so we are dividing by n for k minus 1. So, k minus 1 into n plus n plus 1 divided by k minus 1 plus 1. So, this will come as a n plus 1 by k, and this first 3 cycle of divide by n, the divider frequency is given by f rep n plus 1 by k into f, which is greater than f rep. So, this is how the division will happen in the fractional and PLL. Now, in order to get rid of these fractional spurs, what you need is a because here we are making n times and n plus 1, and if we can make the combination of n and n plus 1, which will help us to reduce these fractional spurs, and one of the method that is widely used is a noise shaping, and this noise shaping is one of the method by which we can able to reduce this fractional spurs. So, one very common and elegant technique to deal with the fractional spurs is exploiting the noise shaping concept, which is widely used in a data converter. So, the periodicity of the control voltage could be broken if the divider modulus is randomly selected n and n plus 1, but still maintain the desired average value. So, the deterministic spurs appearing as a tones will be converted to noise spreading around the VCO signal with a total energy remaining the same. So, f out, which is equal to f out n plus bt, where bt is given by alpha plus qt, and that f division will be given by f out by n plus alpha plus qt, which is equal to f out by n plus alpha and 1 plus qt by n plus alpha. So, this is a how we can make a fine fractional division by using this method. So, this is what is a fractional and PLL. Now, in fractional and PLL, you required a different kind of dividers, and that will divide the fractional, means that can be considered, that can be written as a MDD, du DMD. So, it is a dual modulus divider, and dual modulus divider can be made by using a D flip flop and combination of few simple gates. So, if we do this, we can make a various dual modular divider. So, there is a this can also be extended to the digital PLL. So, this is how we will lead the same PLL, whatever we have designed, whatever we have discussed, we can also make a digital PLL. So, what is the limitation of analog PLL? So, depending on the noise requirement and the reference frequency, the loop filter size can be large, and the capacitor scales with the technology, and their size still does not reduce as favorable as the digital gates, because in digital we can use the digital gates, and a large charge pump current is often required to achieve a low in band phase noise, and power factor phase frequency detector and charge pump linearity could be concern for certain application. So, there is an important trade off between a noise contribution of PLL building blocks, particularly VCO and delta sigma modulator. So, what we can do is this block diagram will look same, only the difference is PFD will be replaced with the TDC. This is a time to digital converter. This is a phase frequency detector will be converted to time to digital converter. It required, instead of RC, it is required a digital loop filter, and then VCO, digital control oscillator can be used, and AMD already it is a digital circuit, that is a modular divider, and then it will be provided to the reference. So, this is how the digital PLL can also be made by by using the same analogy of a analog PLL, and the TDC is nothing but the combination of ADC with the delay. So, that will provide the time to digital conversion. So, this is how the in all these 2-3 lectures we have discussed about the basic PLL, type 1 and type 2 PLL. We also discuss about the frequency synthesizer, fractional-n synthesizer, and the digital PLL. So, if you are interested for more in detail, you can go through the reference, and there is a separate lectures on the PLLs are available. You can go through the same. Thank you.